Welcome to the Explainer. Today, we're initiating a virtual deep-to-shore probe mission to decode the massive physical forces governing our blue planet. Let's get right into it.
So, what invisible mechanisms are actually churning the 71% of Earth's surface that's covered by oceans? I mean, it's not just a giant basin of water sitting there, right? It's a completely active, highly dynamic engine.
To figure this out, our mission briefing is going to take us from the ocean floor up through the ocean layers and circulation into the science of tides and wave dynamics before finally hitting shoreline zones and looking at how our coastlines are changing.
Okay, let's kick things off with Phase 1, mapping the ocean floor.
You know, it's easy to picture the ocean floor as just a flat expanse of sand, but it's actually an incredibly dynamic landscape. We've got continental margins dropping way off into deep ocean basins, holding insanely flat abyssal plains and deep plunging trenches. And cutting right through the middle of all of this, the mid-ocean ridge. It's a massive volcanic mountain system that stretches over 43,000 miles. That literally makes it the longest mountain range on Earth, and it's completely underwater.
Moving right along to Phase 2, let's talk about ocean layers and circulation.
Now, there's a really fascinating inverse relationship going on between temperature and salinity. Basically, warm, less salty water just sits right on top. But as you travel deeper, you hit these rapid transition zones. First is the thermocline, where the temperature just absolutely plummets. Then you have the pycnocline, which is where the density rapidly increases. Together, these create really distinct physical barriers that actually prevent deep and shallow waters from mixing.
This means we've got two completely different engines driving our oceans. On the surface, you have gyres. These are pushed by prevailing winds and steered by the Earth's rotation. That's the Coriolis effect you've probably heard of. But down below, it's a whole different story. You have these deep, dense, cold currents slowly creeping along, driven entirely by those differences in temperature and salinity.
And those deep thermohaline currents effectively act as a massive global conveyor belt. It's an incredible heat engine that overturns the entire world's oceans. Think of it like this. As warm water moves up to the poles, it cools down, gets saltier, sinks, and then creeps along the ocean bottom. This is absolutely crucial for distributing vital heat and nutrients all across the globe.
Which brings us to Phase 3, the science of tides.
Tides are all about gravity. When celestial bodies align during new or full moons, their combined gravitational pull gives us extreme spring tides. But when the sun and moon are at right angles to each other, their gravitational tug-of-war basically cancels out, resulting in much weaker neap tides.
And depending on where you are on Earth, the daily tidal heartbeat falls into one of three distinct rhythmic patterns. You might experience a diurnal pattern, which is one high and low tide a day. Or maybe semi-diurnal, which gives you two equal cycles. Or you could have a mixed pattern, featuring two cycles of varying heights every single day.
Here's something wild to think about. The friction from all these tidal bulges dragging along the seafloor actually acts as a planetary brake. It is actively slowing Earth's rotation down by 1.7 milliseconds every single century. No way, right? But it's true.
All right, ascending back to the surface, let's hit Phase 4. Understanding wave dynamics. So while waves look like giant moving walls of water, they are actually just circular oscillations of energy passing through the water. Out in the open ocean, storm waves are completely chaotic, but over long distances, they actually sort themselves out by their wavelength through a process called wave dispersion.
The magic metric here for our wave base is exactly 1/2 of the wavelength. Below that specific depth, the ocean is completely undisturbed by the chaos happening up on the surface. Seriously, no matter how big a storm is raging above, if you dive deeper than half the horizontal distance between two wave crests, the water down there is perfectly calm.
Let's follow those waves right up to the coast for Phase 5, shoreline zones and currents.
Imagine our virtual probe traveling through 4 distinct transition zones. We start in the deep offshore waters, where waves don't even touch the bottom. Then we move into the nearshore surf zone, where friction suddenly causes them to break. After that, the water rushes up the foreshore beach face, before finally ending at the dry dunes of the backshore.
As these waves hit shallow water, something called refraction causes them to slow down, bend, and strike the beach at an angle. The water washes up diagonally, but then gravity pulls it straight back down. This constant sawtooth motion creates a massive, persistent river of sand moving parallel to the beach. We call this longshore drift.
But if waves are pushing water directly onto the shore, all that piled up water eventually has to escape.
It channels back out to sea in powerful, dangerous rip currents. This is exactly why lifeguards always tell you to swim parallel to the shoreline if you get caught in one. You literally just have to step out of that narrow, fast-moving return flow.
And finally, let's zoom out for Phase 6, changing coastlines.
Depending on factors like tectonic uplift or glacial melting, a coastline is doing one of two things. It's either an emergent coast rising from the sea, which carves stark cliffs, isolated sea stacks, and arches. Or it's a submergent coast, where rising water floods river valleys, turning them into estuaries and fjords, and builds up sandy barrier islands.
Of course, there's a constant battle between human infrastructure and natural sediment flow. It's a real tug of war. Every concrete groin or jetty we build completely interrupts that longshore drift we talked about earlier. It traps sand on one side, but completely starves the beach on the other. Even offshore breakwaters cause sand to build up behind them, creating temporary land bridges known as tumbelows.
So, when we step back and look at Earth's overall coverage, we are overwhelmingly a saltwater blue planet. Get this, only 1.2% of our planetary water budget is fresh surface water. Meanwhile, a massive 71% of Earth's surface is covered by ocean. That makes the mechanics we've explored today, the waves, the currents, and the tides, the absolute dominant surface forces on our entire planet.
I'll leave you with this thought to ponder, long after this explainer ends. The coastlines we've mapped today, they're really just a temporary snapshot in Earth's deep geological time. As tectonic shifts and global temperatures continue to alter sea levels, how will this ever-shifting boundary between land and water redraw the map of our future? Thanks so much for joining me on this exploration.